Hello, my name is Ethan Hong, and I am going to talk about the simulation of many-body and Anderson mobilizations today. To go through, we have multiple steps. We're going to talk through thermalization, quantum mechanics, many-body localization, and then our process on simulations for the Anderson. Now, we're going to start with thermalization. What is thermalization? Thermalization is kind of a way where it exists in classical and quantum physics. When something thermalizes, it spreads energy evenly. We could use kind of like an example shown on the photo above as coffee and milk slowly mixing together. It's going to slowly be able to incorporate any original identity or identity that it had before is eventually becomes lost. Now for this project, we're trying to see if we can prevent thermalization. Why? Well, thermalization erases a lot of the information that we could hold, and we would like to preserve that information. Now, to introduce into quantum mechanics in general is on a very small scale. It's very much subatomic and behaves completely different from our current or classical physics. Stuff like Newton's laws or any laws you would know don't seem to apply in this case. And one of the big formulas I've used in this situation was using Schrodinger's equation, which we had to use later to simulate dynamics. One way we could probably talk about it or how we would use it is the example of Schrodinger's cat, where we have a half chance of it being alive or dead. Trade-off. Now for many-body localization, it's very complex, but in general, we can say this in drawing of a mountain range or a mountainous energy levels, and the blue dot will be an electron that's kind of sitting there. In an MBL or a many-body localization or localized state, the system fails to thermalize or it doesn't have like any much of thermalization. So energy stays the same, it's locked. The information stays the same and nothing changes. You can think of it as an ice cube that never melts, or as an example at the bottom. If you spray perfume in the corner of a room, now you leave for no matter how long, weeks, months, years, stay the same. Nothing's going to change, never mixes. Now, to actually dive into our experiment, we use Jupyter Notebook, SciPy, NumPy. Well, all of you guys also use that as well, so makes sense. But here we decided to use Anderson localization, which developed by Philip Anderson in 1958. It's a much simpler version that uses one electron to start off with. The main difference between those two is that Anderson has a single particle and it doesn't have to interact with anything else or any other electrons or particles, unlike many-body, which will collide and interact, have an effect on each other. An example here I can read out, which is think of it as we're walking across a field, the ground is covered in a random deep hole in tall hills, eventually falling to a hill, and you pretty much end up you can't climb out of it. In this case, the electron falls into the valley between huge or weighs big energy hills that they can't fall out of, and pretty much it stays there. To investigate, we use the time-independent Schrodinger's equation to work with this, and for pretty much picturing it, this is what an electron landscape could look like. It's really disordered, really random, looks in a way still like a mountainous landscape. Okay, so this is what we use to generate our electrons first. We have graphs, really high peaks for our probability. These probabilities are for where the electrons are at that point, or probability of the electron existing at that state. We have multiple disorders. I use disorders from 1 to 10, so 1, 5, and 10, running through multiple of them. And consistently in multiple states as well, there's always one single spot for probability to stay. To work with that, we use multiple as well. I use RNG, so we have C20, C50, but it's for like multiple generations. Now, the only way we're going to find out if it works or not, we want to see if it shifts over time. Under time units, no specific time, but through these units, we want to see if the trend stays over time. Trend is shown here with the blue lines being our original and the orange line being our shifted afterwards. Now, through all these 6 graphs, which 2 different randoms and 3 different disorder values, you can collectively see that there is going to be a general trend between all of them. that you're very much the same. There's still a peak is there, it's quite obviously there. And student stays pretty much identical. So if this proves, the simulation proves right, we will be able to see that the system does not thermalize.
You learn any new skills or?
So it's more of a lot of the information being taught because this is kind of like something new here. So I had a lot of textbook reading beforehand to get like an idea behind to understand it and be able to use that while writing code and writing as a simulation.
Do you think this is something you'd like to pursue?
It could be really a possible option or something I would be willing to learn.